So, welcome everyone. Let's quickly have an introduction to the convex optimization tool CVX that we will use for writing down the LMIs. And as an example, let's look at the stability question for such an autonomous system. We have this autonomous system given to us in the form of matrix A. We know that this system is stable, or rather exponentially stable, if and only if there exists a positive definite matrix P such that ATP plus PA is negative definite. So that's our LMI, and we will shortly code this up in CVX. So one thing to note for this example is that this is a homogeneous linear matrix inequality, and what that means is that if P satisfies the LMI, then so does epsilon P for any positive epsilon. Why am I saying this? That's because strict inequalities are not recommended numerically. So we want to convert this into a non-strict LMI. The standard procedure could be to define some tolerance, and then instead of posing P positive definite, we say that P is greater than or equal to tolerance times identity, such that A transpose P plus PA is less than or equal to minus tolerance times identity. So that would work as well, but because we have a homogeneous LMI, we can in fact show this one. So if such a P exists, if a P positive definite exists such that A transpose P plus PA is negative definite, we can show that a Q exists with this seemingly much more stricter LMI. A quick proof of that would go something like this. So let's call this 1, let's call this 2. So 2 clearly implies 1 because we can just choose P as Q greater than identity, which is obviously greater than 0, and then we have ATQ ATP plus PA is minus identity, which is negative definite. So that's clearly true. Now in order to show that 1 implies 2, observe that if P positive definite exists such that ATP plus PA is negative definite, then the maximum eigenvalue of P, the minimum eigenvalue of P is positive, and the maximum eigenvalue lambda max of ATP plus PA would be negative. So that's because all eigenvalues of this are negative, and the maximum one then also has to be negative, and for this all eigenvalues of P are positive, so the minimum one has to be also positive. Now we can just define epsilon as the minimum of lambda min of P, which is positive already, and so we can define this just as an absolute value. So this is already positive, so the absolute value won't matter, but here it would. So we choose epsilon as minimum of these two quantities in absolute value. And once we do that, we have that P is then greater than or equal to epsilon I, such that A transpose P plus PA is less than or equal to minus epsilon I. So an easier way to see this, let me write this again, is to do this. P is greater than or equal to lambda min of P I, and ATP plus PA is less than or equal to lambda max of ATP plus PA times I, and epsilon is defined as the minimum of these two values. So epsilon has to be less than or equal to this and less than or equal to this. So this is less than or equal to this, and because lambda max is negative, then this is less than or equal to minus epsilon I. And now we can just define Q as P over epsilon to have Q such that ATQ plus QA is satisfying this LMI. So we will code this one in CVX. So let's have a look at the MATLAB code now. I will bring it here. So that's the code. We define two example matrices A, which are and another one this one, and we first find the size of A, and then here begins the CVX part. We first say that this is a semi-definite program, which is basically another term for constraints in the form of linear matrix inequalities. We define the variable P, which is what we want to find, as an n by n matrix and symmetric. You can define the CVX precision as high, medium or low, and I will not go into the details of this, but this governs the stopping criterion for the optimization. And now because we don't have anything to minimize, we are solving basically this problem. So minimize 1 subject to the existence of a matrix P greater than identity such that PA is less than minus identity. And that's because we are solving a feasibility problem, in the sense that we don't want to minimize anything, but we just want to find a matrix P that satisfies the constraints. So we just say minimize 1 subject to these constraints here, so that is just A transpose P plus PA less than or equal to minus identity and P greater than or equal to identity. And that's it. In the CVX status you get the outcome of the optimization, says solved, and if it says solved, then you can check the eigenvalues of P and print them. Similarly check the eigenvalues of A transpose P plus PA and check if they are negative. So these eigenvalues should be negative and these eigenvalues should be positive. So that's it for the introduction to CVX. Thanks a lot.